A cluster looks generous. Empty machines, spare CPU, memory sitting idle. Then a pod lands on the wrong one. Not because the cluster is full, because any available node was never a good enough instruction. A GPU job wakes up on a cheap general node. A latency-sensitive service shares a disk with a noisy neighbor. A regional workload sits 2 time zones away from its users. The application is running. The placement is a quiet failure. This is the stake. Kubernetes can start containers anywhere, and anywhere is how you lose performance without a crash. Node affinity exists because someone had to write a rule that the scheduler could not shrug off. The question that opens the whole story is simple. How do you tell a cluster, with precision, which machines a pod is allowed to live on? Before the rule, you need the stage. A node is a physical or virtual machine that runs one or more pods. It is the actual computer, CPU, memory, disks, network, sometimes a GPU, sometimes a particular rack in a particular data center. A pod is the smallest deployable unit in Kubernetes. It is the wrapper that holds your containers. You do not usually pin a container by hand to a host name. You declare a pod, and the scheduler chooses a node. That choice is the whole game. If the scheduler only asks, "Is there room?" it will fill the cluster like a hotel clerk filling empty rooms. That is fine until the rooms are not interchangeable. Some rooms have extra power, some sit in a different city, some are reserved for production. Node affinity is the language that turns those differences into scheduling facts. Without it, the cluster is a bag of identical boxes. With it, the boxes keep their identities. Node affinity is the ability to assign a pod to a specific node or a group of nodes based on criteria you declare. It is a feature used to guarantee that particular pods land on particular nodes. The guarantee is not magic. It is a set of rules about node labels. You express requirements and sometimes preferences about where a pod should be scheduled. Those conditions can include attributes of the node, anti-affinity style avoidance of certain nodes, and more complex label expressions than a single exact match. Think of it as a passport check at the door of each machine. The pod presents a claim, the node presents its labels. If the claim is required and the labels do not match, the door stays shut. If the claim is only preferred, the door can still open elsewhere. The payoff of this idea is control, better resource management, and a path toward performance that is not left to chance. The next problem is obvious. What exactly is the scheduler reading on the node? It is reading labels. Node labels are key value pairs attached to Kubernetes nodes. They describe characteristics, hardware capabilities, geographical location, environment, or any other metadata you choose to write. Labels organize and categorize nodes, production versus staging, GPU versus general, east versus west. They are essential because affinity, anti-affinity, node selectors, and other scheduling constraints all hunt through those pairs. Without labels, affinity has nothing to match. With them, you get a flexible grouping mechanism. You can target nodes by different criteria and allocate work more efficiently. A label is not a lock by itself, it is a name tag. The lock is the affinity rule that says, only nodes whose name tags look like this. So the cluster's story splits in two. First, someone must label the machines honestly. Second, someone must write a rule that the scheduler will obey. The next chapter asks how strict that obedience can be. There are 2 everyday voices in this story, and then a third, more severe one. Required node affinity says which pod needs which node. The specification can be driven by CPU, memory, a region, a data center, or any special label the node carries. Preferred node affinity is softer. It suggests that a pod should, whenever possible, land on a node matching a label. If no such node exists, the pod can still be scheduled elsewhere. Kubernetes names 3 types: required during scheduling, required during execution, required during scheduling, ignored during execution, preferred during scheduling, ignored during execution. Those long names are not decoration. Each one encodes 2 questions. Must the match exist at the moment of placement? And if the node's labels change later, does the cluster still care? The tension of the whole documentary lives in that second question. Placement is a decision. Runtime is a life. They are not the same. Start with the hardest rule. Required during scheduling, required during execution. This is a hard rule in both directions. The pod must be scheduled on a node that complies with the affinity criteria. If no node in the cluster satisfies the rule, the pod remains unscheduled. It waits, it does not quietly settle for second best. And if the node labels change later, the pod will be evicted. The YAML lives under affinity, then node affinity, then that long required name. Inside, node selector terms hold match expressions, a key, an operator such as in, and a list of values. The label key-value pair in those terms prevents the pod from landing on nodes that lack it. Imagine a lease that is checked at move-in and checked every month after. If the building loses its license, you leave. That is the character of this rule. It is rare in day-to-day manifests compared with the ignored during execution cousin, but it shows the full ambition of the idea. The match is not a one-time handshake, it is a continuing condition. The cost of that ambition is disruption. Eviction is a plot twist the next type refuses to write. The second hard rule is the one most operators actually write. Required during scheduling, ignored during execution. The pod is scheduled only if its required expressions match the node labels. If nothing matches, the pod stays pending. That part is still strict. Here's the twist. If the node labels change later, the pod is not evicted. The scheduler was a gatekeeper at admission. It is not a warden afterward. The YAML path is the same family. Affinity, node affinity, then required during scheduling, ignored during execution, then node selector terms, then match expressions with a key, an operator, and values. This is precision at deployment and permanence afterward. You get a guarantee that the first home was legal. You do not get a promise that the home will still look legal if someone peels the label off the door. That is useful. Workloads keep running. It is also a blind spot. A node can stop being blue in metadata while still hosting every blue pod you carefully placed. The story will return to that blind spot. First, the scheduler needs a softer voice. Preferred during scheduling, ignored during execution is a soft rule. It names a primary way to choose a node according to the affinity rule, but it will not hold a pod hostage. If none of the cluster's nodes match, the pod is still scheduled on a different node. The YAML uses a list. Each item has a weight and a preference built from match expressions. A weight of 100 is a strong nudge. A weight of 1 is a whisper. The scheduler scores candidates. Matching nodes get a boost. Non-matching nodes remain eligible. This is the diplomat in the family. Required affinity is the law. Preferred affinity is the recommendation letter. Use it when you want GPU nodes if they exist, but you would rather run than wait forever. Use it when best effort locality is enough. The ignored during execution half still applies. Once the pod is running, later label changes do not bounce it. Soft at birth, quiet at runtime. The next rivalry is not among these three types. It is between this whole language and an older, simpler one. Before Affinity, there was the node selector. Both ideas try to control which nodes receive which pods. A node selector is a collection of key-value pairs in the pod specification. Only nodes whose labels match those pairs receive the pod. It is exact. It is simple. It shines when the cluster is small and you just need this pod on that labeled machine. Node affinity is the more capable method. It lets you write complex rules, require a label, prefer a label, combine expressions, even express anti-affinity so pods are not scheduled onto nodes with certain labels. When the cluster is large and you want precise control, affinity is the tool. So the difference is not fashion. Node selector is a checklist of exact matches. Node affinity is a grammar. Checklists fail when the sentence you need is prefer production, require SSD, avoid the canary pool. Grammar can say that. The hook is this: if you only ever needed one exact pair, why did Kubernetes grow a whole nested tree under spec affinity? Because placement stopped being a yes or no. It became a strategy. There is a second confusion waiting in the wings. People hear affinity and think of other pods. That is pod affinity. Node affinity is about machines. Pod affinity defines rules for a pod's attraction or repulsion toward other pods. Its scope is colocation, same node or across nodes depending on topology. It is flexible about relationships between workloads. An example, keep pods of the same application together for locality. It operates at the pod level. Node affinity specifies scheduling rules based on node labels. Its scope is the machine's identity, GPU labeled, region labeled, color labeled. An example, schedule pods that need GPUs only onto nodes labeled with GPU resources. It operates at the node level. Same family word, different opponent. One asks, who else is already living here? The other asks, what kind of house is this? Mix them up and you will debug the wrong layer for hours. Keep them separate, and the cluster's social life and its real estate stay distinct. Next, why bother with the real estate rules at all? The advantages are not abstract. Better resource utilization, pods land on nodes that actually have what they need, and application performance can improve. Increased control, administrators can place work that requires specific hardware or network resources instead of hoping the default scheduler notices. Improved availability, by steering pods onto particular nodes or groups of nodes, you can keep an application where it can survive and serve. Picture three outcomes: a machine learning trainer that always finds a GPU, a payment service that stays in the region the regulator requires, a cache that sits next to the disks it was sized for. None of those are guaranteed by spread the load. They are guaranteed, or at least strongly shaped, by labels plus affinity. The source is clear. This is how clusters make better use of themselves. But every control surface has a shadow. The next chapter is the cost of being precise. Complexity is the first cost. Node affinity can make a cluster harder to reason about, especially for administrators still learning the platform. Troubleshooting placement becomes a hunt through nested YAML. Overhead is the second cost. More configuration, more maintenance. You are no longer letting the scheduler sprinkle pods as it sees fit. Limited scalability is the third. Affinity can make it harder to grow. Adding new nodes that meet the same criteria may be difficult or time-consuming. If every production pod requires color equals blue and you add a dozen unlabeled machines, they are invisible to those pods. Capacity exists. The rules refuse it. That is the paradox of a good fence. It keeps the right things in. It also keeps the right things out if you forget to hang the same tag on the new gate. So affinity is not free intelligence. It is a contract you must keep as the cluster changes. Before we walk the contract and commands, one more family portrait: affinity among pods themselves. Pod affinity, intra-pod affinity, and anti-affinity are three different answers to a social question: who should live near whom? Pod affinity schedules a pod with requirements about placing it on the same node as related work or onto other nodes according to topology. The use case is co-location of related services to optimize communication and resource use. Front-end and back-end on the same node can cut network latency. Intra-pod affinity is about containers inside a single pod, preferences to co-locate or avoid co-location of those containers based on dependencies. High-speed inter-process communication is the classic example. Anti-affinity discourages co-location. It spreads pods across nodes or even containers within a pod to avoid a single point of failure. Multiple instances of a critical service should not all sit on one machine. In the Kubernetes API, pod affinity is pod affinity. Anti-affinity is pod anti-affinity. Intra-pod affinity, as the source notes, is not a separate API object in the same way. Node affinity never asked who the neighbors are. It asked what the building is. Keep that distinction when you debug a pending pod. The pending pod might be lonely, or it might simply be in the wrong kind of house. Now the story becomes a procedure. How do you actually assign pods to nodes with node affinity? 5 steps in order, because skipping one is how clusters fill with pending pods. Step 1. The cluster must be running, with a control plane and worker nodes. Affinity is not a local flag on your laptop. It is a conversation with a live scheduler. Step 2. Label the nodes with the specifications that will make placement easy. The command is kubectl label nodes, then the node name, then a key equals a value. Step 3. Define node affinity in the pod YAML. under spec. The nested path is affinity, node affinity, then typically required during scheduling, ignored during execution. Then node selector terms, then match expressions with a key, an operator, and values. Step 4, apply the file with kubectl apply-f and the file name. Step 5, verify with kubectl getPods-o wide. Wide is the part that matters. Default getPods will not show you the node. Wide shows the machine. That is the evidence. If the evidence is wrong, you do not have a running success. You have a story that still needs a label. Labels deserve their own close-up. Adding a label to a node is attaching extra metadata. That metadata can be used for selection, scheduling, and grouping. The command is the same shape every time. kubectl label nodes, the node name, the key, an equals sign, the value. Then you verify. Seeing existing labels uses kubectl get nodes -- show - labels. Setting a new label uses kubectl label nodes with a name and a pair. This is the honest work behind every elegant YAML tree. If color never equals blue on any machine, no amount of required affinity will invent a blue node. The scheduler is not a magician, it is a matcher. Matchers starve without inventory. In a small cluster, you might label by hand. In a larger one, the same idea scales into pools. Production, GPU, Zone A. The sensory detail is a sticker on a server door. The digital version is a key value pair in the node object. Peel the sticker later, and depending on your affinity type, the tenant may stay or may be forced out. That is why labeling is not janitorial, it is policy. Schedule a pod with required node affinity, carefully. First, identify the node you want and know its labels. Second, write a pod manifest. API version v1, kind pod, metadata name such as pod with required affinity. Under spec, affinity, node affinity, required during scheduling, ignored during execution. Node selector terms, a list, match expressions, a key, operator in, values. Then containers, a name, an image such as ngnx latest. Third, apply with kubectl apply-f pod-with-required-affinity.yaml. Fourth, verify with kubectl getPods-o wide. If the labels match, the pod should land on that node. If they do not, the pod waits. Pending is not a crash. Pending is the hard rule doing its job. People treat pending as failure. In this story, pending is integrity. The cluster refused a lie. The pod would rather sit in the queue than live in the wrong house. That is the moral of required affinity, told in 4 kubectl steps and 1 nested block of YAML. Preferred affinity will tell a more flexible moral. Same ritual, softer ending. Preferred affinity uses the same opening moves. Identify the node label you hope to match. Write a pod named, for example, pod-with-preferred-affinity. Under spec.affinity.nodeAffinity, you now write preferred during scheduling, ignored during execution. It is a list. Each item has a weight, then a preference, then match expressions with a key, operator, and values. The source example uses weight 1. The earlier type discussion used weight 100 as a strong preference. Weight is a score, not a veto. Containers again can be nginx latest. Apply the file, verify with wide output. If a matching node exists, the scheduler will tend to choose it. If not, the pod still runs somewhere else. That is the diplomatic ending. Required affinity would have left the pod pending. Preferred affinity would rather see the application breathe. Choose required when wrong placement is worse than waiting. Choose preferred when waiting is worse than imperfect placement. The YAML difference is small. A list, a wait, a preference wrapper. The operational difference is enormous. One blocks, one shrugs, then proceeds. Here is a complete assignment walkthrough with real names from the source. Step 1. Label a node. kubectl label nodes node-1 environment equals production. That pair is now a fact on node-1. Step 2. Write a pod named my-pod, a container named my-container, image nginx. Then affinity, node affinity, required during scheduling, ignored during execution. The match expression key is environment, Operator in, values production. Notice the path. The affinity block lives in spec alongside containers. Step 3. kubectl apply-f pod.yaml. Step 4. kubectl get pods-o wide. If node-1 still wears environment production, my-pod should appear there. This is the smallest complete story the source tells. One label, one required rule, one apply, one verification. It is also the template for every larger story. Swap environment for color. Swap production for blue. Swap my-pod for a deployment with 3 replicas. The grammar does not change, only the nouns do. The hook is already visible. What if you need 3 copies, not 1, and you want all of them on a single worker named node-01? The source's worked example begins with a deployment, not a lonely pod. Name, blue. Image, nginx. Replicas, 3. 2 approaches exist to create it. For simplicity, the source uses an imperative approach, then checks that the deployment exists. The cluster in the example has 2 nodes, the control plane and node 01. The goal is not spread across both. The goal is the opposite of naive high availability. Place the pods on node 01 only. The affinity type is required during scheduling, ignored during execution. The key is color. The value is blue. You edit the deployment and add the affinity block at the same level as the container specification inside the pod template. That last detail is where people fail. Affinity on the deployment object itself at the wrong indentation is a silent no-op. Affinity must ride inside the pod spec the scheduler actually reads. 3 replicas, 1 hard rule, 1 color. The cluster is about to stop being democratic. Node 01 is about to become a neighborhood with a dress code. The configuration belongs in spec, under affinity, under node affinity, under required during scheduling, ignored during execution. Node selector terms, match expressions, key color, operator in, values blue. That is the entire lock. In is the operator that says the node's color must be one of the listed values. Here the list has a single item, blue. After you update the configuration, the pods run on node 01. The source shows a check of the configuration, then placement evidence. All pods of the blue deployment sit on node 01, not because node 01 is the only machine with spare CPU, because node 01 is the machine whose label satisfied color in blue. The closing evidence is not a theory, it is a placement result. A vague preference became a concrete address. This is the scene where the documentary's opening stake is answered in the small. You asked how to tell a cluster which machines a pod may live on. You told it with a nested name so long it sounds like a legal clause, and the cluster obeyed. But remember the clause's second half, ignored during execution. The match was required to get in. It will not be relitigated if color later changes. That timing split is the surprise the source insists on. A required rule controls scheduling. Once the pod is running, later label changes are ignored. They do not trigger rescheduling. Precision at deployment. Permanence afterward. Imagine you paint a door blue, admit 3 tenants, then repaint the door red. The tenants stay, the building's metadata no longer matches the lease, and nobody is evicted. That is not a bug in this type. It is the type's name. Ignore during execution means the running pod is grandfathered. The required type would have evicted. This type will not. Operators who assume labels are live contracts discover this the hard way. They relabel a node to drain a pool, and the pods remain perfectly happy, perfectly misplaced relative to the new truth. If you need the cluster to react after placement, you need a different mechanism than this affinity type. Node affinity, in this common form, is a bouncer, not a security camera. It checks IDs at the door. It does not patrol the dance floor. What did that placement buy? The source's last pages are practical, not romantic. Affinity can improve cluster performance. It can improve resource efficiency. It can reduce contention. It can improve application performance. Those 4 claims are the payoff of the blue neighborhood. When 3 NNGX replicas share node 01 by design, they are not randomly colliding with unrelated heavy jobs on the other node. When GPU pods require GPU labels, they stop wasting trainers on CPU-only machines. When production requires an environment label, staging accidents become harder. Reduced contention is the quiet win. Two noisy workloads on one disk is a fight you can schedule away. Better efficiency is the economic win. Capacity is used for the work it was bought for. The documentary opened on a quiet failure. The app running, the placement wrong. The resolution is a visible success. The app running, the placement intended. Node 01, color blue, required at schedule time. That is not a slogan, it is a verified layout. The remaining question is not whether Affinity works, it is what the cluster should do when the world changes after the layout is already live. So the opening stake is resolved, and then immediately reopened in a more honest form. You can tell Kubernetes with precision which machines a pod may live on. You label nodes. You write node affinity under spec. You choose required or preferred. You choose whether execution will still care. You apply. You verify with wide output. You watch a deployment named blue land entirely on node 01 because color in blue matched. You gain utilization, control, availability, less contention. You also inherit complexity, overhead, and the risk that new unlabeled nodes will not count as capacity. You inherit a timing rule that many people never read. Ignored during execution means the bouncer already went home. If workloads can be placed intelligently, how should clusters respond when conditions change after placement? That is the question the field keeps chasing. Relabeling, draining, disruption budgets, and stronger required during execution ideas are all attempts to answer it. Affinity solved the first mystery, how to mean what you say at schedule time. The second mystery is still open, how to keep meaning it after the pod has already sat down. If you remember only one chain from this story, remember the path the scheduler actually walks. Spec.affinity.nodeaffinity, then a type name that is a whole sentence. Required during scheduling, ignored during execution, or preferred during scheduling, ignored during execution, or the stricter required during execution cousin. Then node selector terms, then match expressions, a key such as color or environment, an operator such as in, values such as blue or production. Labels on the node must already exist or the matcher starves. Node selector was the older exact checklist. Affinity is the grammar that can require, prefer, and avoid. Pod affinity is a different grammar about neighbors, not houses. The evidence at the end of the source is humble and complete. Pods on node 01, benefits named. A remaining unease about change after placement. That unease is the right place to stop. Not because the topic is finished, but because the next true problem is no longer where may I land. It is what happens when the land itself is relabeled under my feet. Until a cluster answers that well, node affinity remains what it has been throughout this story, a precise door policy and a quiet decision to stop checking once you are inside.